Welcome to the Bentley Institute's training course to learn how to perform a modal response spectrum analysis in Staad Pro. A modal response spectrum analysis is a more elaborate type of seismic analysis. Response spectra are plots of maximum response, either acceleration or displacement, of single degree of freedom systems subject to specific excitation. Over the next series of videos, we will show you how to perform a modal response spectrum analysis in Staad Pro, which will include the process to define your dynamic masses and your response spectra load item. We will show you how to specify the maximum number of mode shapes, generate your load combinations, and review the analysis results to ensure that they are in accordance with the requirements of the ASCE 7. For this training course, we will be generating the modal response spectrum load cases for this sample model. In Staad Pro, if I go to the General tab and the Load and Definitions sub-tab, and now I'm going to expand my Definitions group and my Load Case Details section. You'll notice that the seismic load definition and the seismic load cases have already been generated in accordance with the IBC equivalent lateral force procedure for this sample model. We will next generate the seismic analysis for the dynamic load cases, and after that analysis is performed, we will compare the base shear results of the equivalent lateral force procedure with those of the dynamic load cases to ensure that the scale factors are appropriate and in accordance with the requirements of ASCE 7, Section 12.9. The first step that we need to perform in Staad Pro in order to perform our modal response spectrum analysis is to establish the dynamic load cases that will contain the response spectrum load items. In the Load and Definition dialog, I will now highlight the Load Case Details section, and then I'll click on the Add button. In the Add New Load Cases dialog, I will now set up my dynamic load cases. And we will be setting up a dynamic load case to represent our dynamic load in each of our horizontal global axis directions from both a positive and negative. Here I will set up my loading type, set to seismic, and I will create the load case title. Here I will start with dynamic load in the positive X direction, and then click Add, and then I will set up the rest of my load cases. For the negative X direction, for the positive Z direction, and also the negative Z direction. Once I've finished establishing my load cases, I can go ahead and click on the Close button. After we set up our dynamic load cases, we are ready to define our dynamic masses. Within the first dynamic load case, you will define the masses that will contribute to the seismic loading. The masses are specified in terms of weight and in the directions in which they are dynamically active. For the sample model that we will be using in this training, we will include 4 spectrum commands to represent the seismic loading acting in the positive and negative global X and Z axis directions. When more than one spectrum command is used in a model, the mass is derived from the weight definition within the first spectrum load case only. So within our first dynamic load case, we will define our dynamic masses that will be used in the remainder of the dynamic load cases. For this sample model, we will be defining the dynamic mass in terms of self-weight and uniform member loads, and they will be acting in the global X, Y, and Z axis directions. To define our dynamic masses, I will highlight the first dynamic load case, and then click on the Add button. In the Add New Load Items dialog, I will navigate to the self-weight load, and I will be defining it in the X, Y, and Z axis directions. And we are defining this in terms of weights, so we will actually specify a factor of +1 for each of the dynamic masses within the first load case. So I will define the direction in the X direction with a factor of 1, and then click on the Add button. And then I will repeat this process in the Y and Z axis directions as well. I can define the dynamic masses with using a number of different load type items, and we will also be defining some superimposed member loads to be contributing to the dynamic masses as well. Here over in the left pane, I will now select the member load option for a uniform force. Again, I'm going to enter all of my dynamic masses with a positive sign, and I'm going to enter 0.05 kips per foot. And again, I'm going to be specifying this in the global X, Y, and Z axis directions. Once I am done entering all of my dynamic masses, I can go ahead and click on the Close button. And here I can see all of my dynamic masses have been defined, and they are now ready to be assigned to the model. We will first assign the self-weight item to the entire model. I will select the first self-weight item, select the Assign to View assignment method, and then I will click Assign. I will repeat this process for the other self-weight masses. I will also assign the uniform member load to all of the beam members that are actually parallel to the global Z-axis direction. So I will start by highlighting my first uniform load item. I will go up to the Select menu item, and then I will select all beams parallel to the global Z-axis. Then I could just simply say Assign to Selected Beams, and then click Assign. And I can repeat this process for the other masses in this category.